Okay, so good morning, everybody. So today we are going to spend time on what we call the Ito processes and related Ito formulas. Okay, so it will close the chapter 2. Okay, so let me remind, okay, what we have done during the previous session. So during the previous session, we have defined the stochastic integral on L2prog, okay, that is the space of the continuous of the stochastic processes, excuse me, that are progressively measurable and square integrable, okay, for the two variables. So let me remind how we have done the job. So I have first defined the stochastic integral for elementary stochastic processes, okay, in epsilon. Okay, that was defined this way as a kind of analogous of Riemann integral, but where I replace, okay, the way to measure the distance between 2 points, okay, in the case of Riemann integral, you use the classical length, okay, and here you replace this measure by a Brownian increment, okay? So I have this. We have studied the properties of this elementary stochastic integral, and in particular, okay, we have seen that it was linear, continuous, adapted, okay, centered, okay, that it was a martingale, okay, that we are going to be able to compute this kind of quantity here. And in particular, you have this relation here, this relation, that is what we call the Ito isometry. And this relation was fundamental in order to extend our stochastic integral for more general integrals. So just remind that this one was just a consequence of this one, okay, for s equal to 0. I have this. And from this equality here, we have extended the Ito integral for elementary stochastic processes, okay, for more general processes. So it's exactly what I have done here, okay. We have said the following. So in fact, if I consider the mapping that associate to an elementary stochastic process, the process dealing with the elementary Ito integral, okay, we have two things. The fact that we have a mapping that is linear and that is in isometry in the sense that it preserves the norms, okay? And in this way, since the set of the elementary stochastic process is dense in L2prog, okay, using approximation arguments, okay, we were able to define without ambiguity the stochastic integral of an element in L2prog as the limit of the stochastic integrals associated to approximating sequences, okay? And the main point concerning the way to use the isometry is that if I do this, the Ito isometry ensure the fact that this limit doesn't depend on the approximating sequence, okay? So it was the big deal. And passing to the limit, okay, in the properties concerning the elementary stochastic integral, we have proved that the stochastic integral fulfills all these properties. So it is something that is linear. We have a continuous process that is adapted to the Brownian filtration, that is centered, okay, that fulfills the Ito isometry, that is a martingale, and so on and so on. So in particular, just a remark, okay, so this integral extend what we have done in the chapter 1. I have proved this, what I have done in the case of the Wiener integral, or in the case of a special integrand of the form a function of the Brownian motion, as we have done in the chapter 1. And just keep in mind that the main difference between what we have here and what we have in the case of the Wiener integral is that in the case of the Wiener integral, we have a Gaussian process, and here the stochastic integral is a priori no more a Gaussian process. Okay, it's the main difference between the two, but all the other properties are preserved, okay, continuity, the fact that I am adapted, and so on and so on. So today we are going to focus on what we call Ito processes, okay? And what is an Ito process? Okay, an Ito process, so you have the definition 2.3.1 here. What is an Ito process? It is a stochastic process. So first, keep in mind that this process is supposed to be continuous and adapted. When I mean adapted, okay, it's with respect to the Brownian filtration, as usual. Huh? In all this chapter, the underlying filtration is the Brownian one here. So continuous adapted, meaning that, okay, this kind of process is progressively measurable, because when I am continuous and adapted, I am progressively measurable, as we have seen in the chapter 0. So we define an Ito process this way, okay? We have 3 parts, okay, in an Ito process. You have this one here, that is in fact the initial value of this Ito process. That will be a constant, a real number here, because I keep in mind that I have written this here, but F0 is the trivial sigma algebra, so this one is equivalent to the fact that X0 belongs to R, simply. Okay, then I have a Riemann integral. And to give sense to this Riemann integral, I impose, okay, the psi here to be in L2 prog. Why not? Okay, it's in the definition. And if I suppose this, I am sure that all these Riemann integral are well defined. So a constant plus a Riemann integral plus another term. And what is this term? This term is a stochastic integral as defined previously. And we have seen that in order to give sense to this stochastic integral here, we need to impose that phi is also in L2 prog. So when we write the things this way, okay, everything, all the 3 terms are well defined, and we define an Ito process as, okay, a continuous and adapted process having this particular form. Okay, so I have this. So let me see an example of what may be an Ito process. Okay, so what may be an Ito process? Well, of course, maybe the most famous Ito process is the Brownian motion. If I take the Brownian motion, Bt, okay, I can write it in the following way. It is 0 plus the integral between 0 and t, 0 ds, plus the integral between 0 and t of 1 dbs. Meaning that if you have in mind this decomposition of an Ito process, okay, then the Brownian motion is a particular case because it is, of course, continuous and adapted, okay, and fulfill this relation with x0, psi equal to 0, and phi equal to 1, okay? So this one is an Ito process. Okay, so we have this. Now, okay, we have the definition of an Ito process. So just let me introduce notation, okay? So when xt is defined through its Ito decomposition, this way, okay, we have a formula that is a little bit long to write. And in order to shorten the notation, okay, we write this decomposition. So it's a notation. We write the following, okay, we say that d of xt is equal to psi of t dt plus phi of t dbt. So it's just a notation, okay, in order to say that, okay, I have this decomposition, I can write it this way in a compact way. It's in order to avoid to use the integral notation. So it's the kind of dual, okay, differential notation for this integral decomposition, okay? So the first result we are going to see concerning Ito processes is the fact that this decomposition is unique. So up to stochastic equivalence. What is the meaning of this one? Okay, so just let me duplicate this slide here. I am interested in the proposition 2.3.1 here, that is the uniqueness of the Ito, decomposition. So I have the things this way here. I erase. Okay, so what is the meaning of this proposition here? Okay, so I do the proof of proposition, proof of proposition 2.3.1. So I want to prove the uniqueness of this decomposition. So I start from an Ito process. I will consider the first decomposition this way, okay, with the good integrability conditions for sure. And I suppose that there exists another decomposition that I will write with tilde. The meaning of this proposition is that, okay, if you have this, it's what I have to prove. I have to prove that the two constants are equal. I have to prove that psi is equal to, oh, I can write it this way. Psi and, excuse me, so psi and psi tilde are indistinguishable. And finally, that phi and phi tilde are also indistinguishable. This is the meaning of uniqueness to up to stochastic equivalence. So we have to prove this. Here I have x0 tilde here. Okay. So here we prove that when we have this, okay, necessarily I have the equality between all the components of this Ito decomposition. It's not possible, okay, to readjust the decomposition in order, okay, to obtain two different ones that would give rise to the same Ito process. It's not possible, okay? So first of all, so I have 3 points to prove a priori, okay? So this one, and this one. For the first one, it's not complicated because for the first one, okay, I just have to take t equal to d0. That gives me that x0 is equal to x0 tilde. Because when I take t equal to 0 in this decomposition, all the integrals are equal to 0. And so I have the equality between these two numbers. Okay? So I know that x0 is equal to x0 tilde. So from this relation here, I can say that I have this one, the integral between 0 and t of psi of s ds plus the integral between 0 and t phi of s dbs is equal to the analogous with tilde okay, so I have this. In fact, what we are going to do is readjust a little this expression in order to say that I can write it this way, that the integral between 0 and t of psi minus psi tilde of s ds is equal to the integral between 0 and t of phi tilde minus phi, okay, of s dbs. Okay? Why I write this way, okay? So I regroup the Riemann integral and I regroup the stochastic integral. So here what you have a continuous and square integrable martingale. okay, because of the definition of the stochastic integral on L2 prog, okay, that give rise to continuous and square integrable martingales with respect to the Brownian filtration. And here, okay, I have this term here that belongs to L2 prog. The integrand is in L2 prog, and here I have just a Riemann integral. But in fact, we have in the course something in relation with this kind of equality here. So I erase what I don't need here. So I just keep the equality I have at the end here. And I deduce from this one, okay, and from the proposition 0.5.5 of the chapter 0, I deduce that a continuous and square integrable martingale of this form here, okay, that takes the form of being a Riemann integral is necessarily indistinguishable with 0. So if I denote this one by MT, I know that from the proposition 0.5.5 that MT and, okay, 0 are indistinguishable. Okay, so MT and 0 are indistinguishable. Okay, it's a consequence of the proposition 0.5.5. So in particular, okay, if I have this, I have the expectation of M capital T square that is equal to 0. And what is this one? Okay, so it's the expectation of the integral between 0 and capital T phi tilde minus phi of S dbs square. And from the Ito isometry, I know that the expectation of the integral of the square is just the expectation of the integral of the square of what I have inside. It's the Ito isometry that give me this. Okay, and the fact that here I have something that is positive with the expectation of the integral that is equal to 0 implies that phi and phi tilde are indistinguishable. Okay, let's write it. So from the proposition 0.5.5, okay, MT is indistinguishable with 0, from which I deduce that, okay, using here, so here I have the Ito isometry. From which I deduce that from the Ito isometry, this is equal to 0. So I have here the expectation of the integral of something that is positive. Okay, I know that this one has to be positive. When it is equal to 0, it means that what I have inside is 0 with respect to the product measure here. That is exactly the definition of this indistinguishability. Okay, so I have this one, okay, and I have, okay, done the job for the part in the stochastic integral. So for the other part, so now I can erase this one, and I can deduce in the same way that the process integral between 0 and t phi of s minus phi of s tilde ds, okay, is also distinguishable and indistinguishable is 0. Okay, so in particular, you have the integral between 0 and t of phi of s minus phi of s tilde ds that is equal to 0, okay, for any t. You have this one for any t. okay? And here you have a Riemann integral. Okay, so for example, if you compute the derivative with respect to t here, you will obtain that what I have inside has to be equal. That is, the difference has to be equal to 0, because if I have the integral depending on the upper bound that is equal to 0, okay, then necessarily what I have inside has to be equal to 0, okay, for a Riemann integral. Here it's true for any t, it's not for a fixed t, it's for any t, okay? So computing, for example, the derivative that exists almost surely here, okay, almost surely with respect to the Lebesgue measure, then this quantity equal to 0 for any t will give me that I have what I want, that is what I have inside is necessarily equal to 0. So we have the uniqueness in the Ito decomposition, and this uniqueness, okay, is based on a result we have seen together in the chapter 0. That is the fact that when I have a square integrable and continuous martingale that take the form of a Riemann integral, it is necessarily indistinguishable with 0. Okay? So in particular, I have the following corollary. That is a basic consequence of what I have done here. So I erase this. So let's have a look on the corollary. This one here. It tells me the following. If I have an Ito process of this form here, corollary 2.3.1. So if I have an Ito process having this form, okay, I have this Ito decomposition. And if I suppose that I am a martingale, okay, then necessarily this part is equal to 0. So if you have an Ito process that is a martingale, okay, this Ito process will be a martingale if and only if I don't have, so in this situation, if I don't have this part here. So it's an equivalence to proof. So one part is obvious, because if I don't have this part, what is my Ito process? It's just a constant plus a stochastic integral, and I know that a stochastic integral is a martingale from what I have done during the previous session. Okay, so if I don't have the part in dt, then I am a martingale, a square integrable martingale. So what happened if I suppose this one to be a martingale? So let's write it, okay, as MT, where this one is a martingale. Okay, continuous and square integrable martingale. But I can do as I have done previously. I can write that MT, okay, minus the integral between 0 and t, phi of s dbs is equal to x0 plus the integral between 0 and t of psi of s ds. So I have this. And once again here, what you have here, you have a continuous and square integrable martingale. And in fact, I can also, if I prefer, it will be better to write it this way. I erase the constant here and I put it here. Excuse me. Minus x0 is equal to this one here. So here you have a continuous and square integrable martingale, because I suppose that my Ito process here is a martingale. I know that this one is a martingale from what I have done in the previous session, okay? And if I add or subtract the constants, I don't change the fact that I am a martingale. And I have this one that is a Riemann integral. Okay, and once again, if I use the proposition 0.5.5, I obtain that this one is necessarily equal to 0. That is, MT equal to integral between 0 and t, phi of s dbs plus x0, implying that the part in dt want, okay, is equal to 0. Okay? So if you have an Ito process defined this way, okay, that is a martingale, a continuous and square integrable martingale, necessarily you know that the part in dt is equal to 0. You don't have a Riemann integral in the Ito decomposition in this case. Okay, so you will see that it's something that we are going to use in the final part. Okay, so I have proved now that the Ito decomposition, so I have defined what is an Ito process here. I have proved that the Ito decomposition is unique, okay, up to indistinguishability. And we have proved that if an Ito process is a martingale, then necessarily this Ito process has a part in dt equal to 0. Okay. So what is the meaning of this one? The definition 2.3.1. The definition 2.3.2, excuse me, tell you the following. I have defined this kind of object here. So this way. We have defined in the previous session this kind of stochastic integral for theta belonging to L2 prop. Okay, so in the previous session. Okay. My idea now is that I want to give sense to this one. So I want to give sense to the integral between 0 and t of theta of s. So instead of having the Brownian motion, I want my Ito process. So where x is an Ito process with d of xs that is equal to psi of s ds plus phi of s dps. So I want to give sense. I want to give sense to this quantity here. I have a very natural way to do. Okay, so what can I do? I start from what I want, that is this one. Okay, and what it can be, but I know that I have this. Okay, so it's a notation here. It's just the differential notation associated to the Ito decomposition here. But I can plug inside d of xs and replace it by this one. And if I do this, okay, I obtain what? I obtain the integral between 0 and t of theta of s psi of s ds plus, okay, plus what? Plus the integral between 0 and t of theta of s phi of s dbs. Okay, so just using this differential notation and plug it inside what I want to define here. So now I have this natural definition of an integral with respect to an Ito process, but be careful because if I do this, okay, if I want to do this, I need to give sense to all these integrals here. And in fact, okay, I need some hypotheses. So this one is okay if this one is well defined and if this one is well defined. For this one, I can impose that theta phi belongs to L2 prog. And for this one, so keep in mind that I have defined the stochastic integrals for integrands in L2 prog. So if theta phi belongs to L2 prog and theta phi also belongs to L2 prog. And depending on the Ito decomposition of x, okay, so that are this term here and here, it will be more or less restrictive conditions here, okay? Because if I want to give sense to this one, I need that this one is well defined, this Riemann integral is well defined, and that this stochastic integral is also well defined. It's exactly what I have written in the definition here. You have this integrability condition here and here, okay? So you have a natural way to extend what I have done for stochastic integral with respect to the Brownian motion and to extend it to Ito processes through the Ito decomposition. Okay, and the only thing I have to be careful with is the integrability conditions in order to give sense to the Riemann integral part and to the stochastic integral part. Okay, so nothing particular to see here. Okay, let's continue. So now we are going to see a set of formula that are really important. So, okay, that is what we call the Ito formulas. So just let me once again for the moment to remind you what I have done previously. In the chapter 1, we have proved the following. That was the Ito formula for the Brownian motion. Plus 1/2 the integral between 0 and t f second of bs ds. Okay, with so I have supposed that f, okay, is 2, okay, and with f second bounded in this situation. I have imposed I have imposed this, okay? So it was what I have done in the chapter 1. So it was the Ito formula for the Brownian motion. So, and I remind you how I have obtained this result. So let me remind you the sketch of the proof in this to obtain this formula. First, make appear small increments, that is to write this difference here as the sum of little increments. I can write them this way, ti plus 1 over n minus f b ti over n, okay, from I equal to 0 to n minus 1. Okay, so I express this difference using this sum of increments over intervals of size t over n. Okay. In a second step, I apply what? I apply the Taylor formula, the Taylor expansion at the order 2 to obtain Taylor expansion that give me two terms, okay? F prime of b ti over n times b ti plus 1 over n minus b ti over n. And when I will do the sum of these terms, okay, it will converge toward exactly this term here, up to some basic computations, let's say. And I have a second element, my Taylor expansion here, plus 1/2 the second derivative at a particular point that I can define this way here, I n, okay, of by the square of the increment here, this one square here, okay? So you see that the 1/2 come from the Taylor expansion. The second derivative also come from the Taylor expansion. Okay, and if I do the job, okay, so I have explained to you how to do during, it was 2 sessions ago, okay, and you have also the proof in the lectures note. I can pass to the limit, so I can do the sum of this one, and pass to the limit to prove that I converge toward what I want, okay? So make appear increment on small interval, use the Taylor expansion, and then, okay, you have to use, okay, technical tools in order to prove that everything is convergent toward the good limit. Okay, it's what we have. And keep in mind also that here, I obtain a Riemann integral because here, when I consider the square of the increments, okay, I will have quantities that will be related to the quadratic variation of the Brownian motion on an interval. And I know that the quadratic variation of the Brownian motion on an interval of size t is exactly equal to t. And the t, okay, is the one that will give me the dt or the ds exactly here, okay? So what is nice with this kind of formula, okay, is that, okay, using exactly the same sketch of the proof, that is making appear increment on small intervals, then using Taylor expansion, you are going to be able to obtain this formula, okay, for Ito processes. Okay, so it's exactly what is written here. If I have an Ito process, and if I have a mapping, so I have here this integrability condition here to be of class C2 with bounded derivatives, then I have this formula, okay, that is the analogous of what I have for the Brownian motion, what I have proved in the Brownian motion in the chapter 1. So just let me comment this formula here. So I want to do the proof because, okay, I repeat, the sketch of the proof is exactly the same. So have it in mind, okay? It may be a question during an interview for an internship or something like this, okay? You don't need to know all the details, but the way to obtain, make appear increments, Taylor expansion, and then just techniques, okay? Pass to the limit. So let me erase this. And let's have a look on the Ito formula here. So I start from a stochastic process that is an Ito process that is something of this form here. Okay, so I have the constant, I have the Riemann integral part, and then I have the stochastic integral part here. Okay, and this formula tells me the following, that f of xt is equal to f of x0 plus the integral between 0 f prime of xs d of xs plus 1/2 the integral between 0 and t f second of xs phi s square ds, where the phi here, the phi square here is the square of the integrand involved in the stochastic integral part of the Ito decomposition, okay? And I just also keep in mind that this one is what I have defined on the previous slides. That is not this one, but just this one here. I have given sense to the integral with respect to d of xs, okay? It's exactly what I use here. So this one, okay, let's write that it is, to keep in mind, I have this one. F prime of xs psi of s ds plus the integral between 0 and t f prime of xs psi of s dbs. Okay, it's what I have defined in the previous slide here, the integral with respect to an Ito process. Okay, what can I say? I can say that if I am in the case of the Brownian motion, I know that the Ito decomposition of the Brownian motion is this one, 0 dt plus 1 dBt. Okay, so if I apply this formula to the case of the Brownian motion, okay, if I apply this formula to the case of the Brownian motion, so I obtain f of b0, that is exactly f of b0 that is given by this term. I have what? I have the integral of f prime bs dbs. So if I replace xs by bs, I have exactly this term. And then I have this term here. And what happened for this term when I am the Brownian motion? But I know that in the Brownian motion, the phi in the Ito decomposition is just the phi is equal to 1. So phi square is equal to 1. And so that's why I have here this quantity that is equal to this one in the case of the Brownian motion. So you have really an extension of the Ito formula for the Brownian motion here. You have really an extension, okay, for more general Ito process. Okay, so I have this. This is my first remark. Second remark, okay, I have some, let's say, integrability condition here for some regularity condition for f and also some integrability condition for the derivative. I want that the derivatives are bounded. Okay, so why this hypothesis here? Why this hypothesis that is really strong? Huh? Because, okay, I suppose that f is of class C2 with bounded derivatives. Okay, with bounded derivatives. Okay, if I try to find such a mapping, okay, but I have what? I have affine mappings, okay, or mappings that have the same behavior as something that is affine. So in general, okay, it's a little bit complicated to find such a mapping. Okay, typically the mapping x gives x squared doesn't fulfill this condition because the derivative of x squared is 2x, something that is not bounded. So I need this very restrictive condition in order to give sense to the Ito formula. Why I need this? Because keep in mind that if I want to write this, okay, I need that all the integrals involved in the decomposition, okay, are well defined. So it means that I need that this Riemann integral with this integral is well defined, this one is well defined, and that this one is well defined. Okay, so in order to give sense to this formula, I need that f prime of x psi, f prime of x phi, and I need that f second phi s square, okay, fulfills the good integrability condition that belongs to, okay, so for this one, I need to belongs to L2 prog. For this one, I need to belongs to L2 prog. And for this one, so I have this one, and for this one, I can only belong, so not to L2 prog because it's the square here, but L1 prog, let's say. And why it's okay? Because here I do very, very strong hypothesis. If I'm in this setting, okay, f prime and f second are bounded, and I know from my Ito decomposition that psi, phi are in L2 prog, and so phi square is in L1 prog. So in the case where I impose for the derivative to be bounded, I obtain something that is okay, everything is well defined as Riemann or stochastic integral, but the price to pay is that, okay, I have a nice formula, okay, but very, very restrictive conditions on small f, okay? So I can apply it here a priori, but only for very, very particular small f. And we are going to see in a few minutes how to overcome this problem because I want to be able to apply this Ito formula for more general situation than the one where f is of class 2 with bounded derivatives. Okay, I want to enlarge the set of the mapping f in order to be able to write this Ito formula, but I will have a price to pay if I want to do this. and the price I will have to pay if I want to extend this formula for more general small f is that I need to enlarge the set of definition of the integrals involved in this formula. So for the Riemann integral, it's not a problem because I have conditions that I know. But for the stochastic integral, if I want to relax the hypothesis on f for the Ito formula written this way, I will need to relax, in fact, the definition of the stochastic integral. Because for the moment, okay, I have defined the stochastic integral on L2 prog. Okay, if I want to relax the condition on small f in the Ito formula, I will need to relax the integrability condition of the integrand. Okay, so it's exactly what we are going to do in few seconds. Just a remark concerning this other proposition here, but in fact, nothing to say, except the fact that here you have the Ito formula, where when you have a mapping F, okay, so you have F from R into R, that gives to X F of X. Here's just to say that I can do exactly the same thing if I have a mapping not depending on small x, but a mapping depending on time and small x, simply. Okay, so I am interested in f of t xt. Okay, I apply this mapping to my Ito process, and I have the same kind of formula here, the same kind of formula. So there is just an extra term here, and keep in mind that here, what I define as f prime x is just the partial derivative of f with respect to x. Here you have the second partial derivative, and what I define as f prime of t is the partial derivative of f with respect to the time. And why I have this formula? But it's just because, okay, keep in mind that I have explained to you or reminded to you that in the case of the Brownian motion, it's the Taylor expansion at the order 2 I use for f of x. But if you have f of t and x, you have a mapping depending on two variables. You can write the Taylor expansion, okay, for this mapping depending on these two variables. So when you will have, okay, the partial derivative with respect to the second variable, it will make appear this part that is the analogous of this one, okay, and then you will also make appear a term that is that involves the partial derivative with respect to the time, that is this one. Okay, so you have an extra term here that is the partial derivative, a Riemann integral with inside the partial derivative of f with respect to t. That comes from the fact that here, okay, I have a mapping depending not only on x, but depending on the time and on x. Okay, so it's really a basic extension of this one with exactly the same sketch of proof. Make appear increments, use Taylor expansion, and then pass to the limit. Okay, so nothing complicated for this one. Okay, it's the Ito formula, okay, with a time dependency. Okay, so now my objective will be to relax hypothesis on f in order to obtain such formulas. Okay, because here I have the same kind of hypothesis. Huh? I have the same kind of hypotheses that are very restrictive. I am C1 in time, C2 in x, and I want bounded derivatives in order to give sense to all these integrals. Here, I want to relax this set of hypotheses to obtain the same formula as this one, but for more general small f. Okay, so I just do a very small break, okay, and I come back in 1 second. Okay, so let's continue the course. So remind that what I want to do is to be able to relax the hypothesis of integrability in the Ito formula, because for the moment I need f of class C2 with bounded derivatives, something that is very restrictive. Okay, so we are going to introduce new spaces of stochastic processes. So keep in mind that I have defined the stochastic integral for an integrand in L2 prog. Okay, so I remind you that to be in L2 prog, okay, x belongs to L2 prog of omega times 0 capital T means that the expectation of the integral of the square is finite. Okay, so I am progressively measurable. Expectation of the integral of the square is finite, meaning that I am square integrable with respect to the product measure, okay, on omega times 0 capital T. So we are going to define two spaces that I will call H2 lock and H1 lock, okay? So what is it? In fact, H2 lock for local, and I will explain just after, is just the set of the stochastic processes on 0 capital T that are, so I need progressively measurability, okay? Always, so progressively measurable, and such that, so I will relax a little the integrability condition, and instead of having expectation of the integral of the square that is finite as a number here, I impose the integral between 0 and capital T of xs squared ds. So here you have a random variable, and I want this random variable to be finite p almost surely. I want it to be finite p almost surely. Okay, so the 2 you have here, the H2 here, the 2 in H2 notation means that I have a square here. It's the 2 here, that is the 2 here. I can also define H1 lock. And if I define H1 lock, instead of having the integral of the square, I have just the integral of the absolute value. That would be finite p almost surely. So I define H2 lock and H1 lock this way, okay? The set of the stochastic processes that are progressively measurable. So for H2 lock, I need that the integral of the square is finite p almost surely. In H1 lock, the integral of the absolute value is finite p almost surely, okay? So obviously, as usual, I know that L2 is included in L1. So I have H2 lock that is classically included in H1 lock. I repeat that L2 is included in L1, and here I have a condition with the integral of the square, here the integral of the absolute value. Okay, so it's just a simple consequence of the Cauchy-Schwarz inequality that if I fulfill this one, then this one is finite, okay? Cauchy-Schwarz inequality because I do a Riemann integral on a compact set here. So this one is always true. And what is more, I know that if the expectation of the integral of the square is finite, necessarily, it's something that is a result from probability theory, that if you have a random variable with an expectation that is finite, necessarily this random variable is finite p almost surely. So if I have the expectation of this integral that is finite, it implies that necessarily what I have inside the expectation, that is this integral here, is a random variable that is finite p almost surely. And so this consequence here ensure that if I am in L2 prog, then, so if I fulfill this, I fulfill this, so I am in the space H2 lock. So I have these inclusions here, the one I have written here, okay? So L2 prog included in H2 lock, included in H1 lock. Just a remark here, because it's something that we are going to do, okay, and to use in the financial part. So here, okay, my expectation here, I can write this expectation here as, so it's an expectation with respect to the probability p, okay? And I can write this one as the integral over omega integral, it's like a double integral because it's expectation of the integral, xs square ds dp. So be careful because you have here something that strongly depends on the choice of p. If you change the initial probability, in general, you change the integrability. And so this definition here, you can write it this way, it depends on the choice of p. Okay? But it's not totally true for the definition of H1 log and H2 log. Why? Suppose that you consider a probability Q that is equivalent to P. This notion is equivalence. I have introduced it at the end of the chapter 0. It means that, okay, Q of A equal to 0 if and only if P of A equal to 0. So they have the same negligible sets, in fact. Okay, so Q equivalent to P means that they have the same negligible sets. So it means also that if I have a set of probability 1 for one Q, okay, it will be the same for P. Okay, so I have this. And what is interesting is to say that this condition here, so the condition in the definition, let's say, for example, of H2 log, this one finite P almost surely means that the probability that I am finite is equal to 1. And if I take a Q that is equivalent to P, this one will be equivalent to the fact that Q of integral between 0 and capital T xs square ds finite is also equal to 1 because they have the same negligible sets. So by complementary set, they have the same set of proba 1, these two probabilities. Okay, so it implies that these two definitions, this one and this one, okay, are definitions independent of the choice of P. Oh, it's not totally true what I write, but up to equivalence, okay? Up to the equivalence between probabilities. So it means that if I change P into a Q that is equivalent to P, I change nothing concerning my definition, something that is not true for L2 prog, because in L2 prog, okay, here, my condition is not to be finite P almost surely, so it's not something in relation with, okay, a set of probability 1 for P, but it's really an integral that has to be finite, an integral with respect to P. If I change P into another one, okay, sometimes, okay, I can be integrable with respect to P and not integrable with respect to Q, even if Q and P are equivalent. Okay, so independent of P, or excuse me, independent of P up to equivalence, independent of P up to equivalence, dependent on P. Okay, and you will see that in the financial part, okay, we will start with the probability P that we will call the historical probability, and you will see that using, okay, some financial definitions and financial arguments, we will make appear a probability Q equivalent to P that we will call the equivalent martingale measure. And what will be nice, okay, later on is that the definition of H1 log and H2 log will be independent of the choice of P or Q, okay? So it was my first remark concerning this, okay? So I have spaces, okay, that are greater and greater this way. In particular, L2 prog is included in H2 log, okay? So we are going to see the next proposition. So for the next proposition, I won't enter into too much details because in fact, you have here the main and the biggest difference between my course and the course done by Bernard de Meyer for the triple MEF program. In the case of the triple MEF program, okay, they study deeply the question of how to extend the stochastic integral for more and more general integrants, okay? I won't do this in details in this course because it is technical. I need the notion of stopping times related to martingales and so on and so on, okay? And I don't want to do. It's out of the scope of my course, okay? What we are going to do is to admit the following proposition that tell me the following. So suppose that at this stage, okay, I have what? So for the moment, I have defined the stochastic integral here, defined as a stochastic process for x belonging to L2 prop. And I have a lot of properties here for this one. I have the fact that I have something that is linear. I have something that is continuous. I have something that is adapted. But I have also something that is centered plus the itoisometry. And I have something that is also a square integrable martingale. Okay. This proposition 2.4.1 tell me that we can extend. So this one may be extended for x belongs to H2 lock. It may be extended for x belonging to H2 lock. Okay. So it's not that simple to prove this. Okay. And I repeat that in order to do this properly, I will need to use, okay, some notion related to martingales, that is the notion of stopping time and of stopped, okay, stochastic processes. It is out of the scope of this course, so we are going to admit this fact here. We are going to admit that we can extend for x in H2 log. I have done the job properly for x belonging to L2 prog, proving all these properties here. We are going to admit that we are able to do the same for this one. But there is a price to pay. There is a big price to pay, okay, doing this extension. We have seen in this proposition here that my stochastic integral fulfills all these nice properties. I am linear, I am continuous, I am adapted to the Brownian filtration, my expectation is 0, I fulfill the itoisometry, I am a martingale, I am able to compute this kind of conditional expectation, and finally that I am a continuous and square integrable martingale with respect to the Brownian filtration. In the case of the extension that I suppose to be possible here, in fact, okay, so in this case, the only properties that will be fulfilled by this extension, okay, will be very small. I will have the linearity, I will have the continuity, I will have the fact that I am adapted to the Brownian filtration, but I won't have the fact that I am centered. I won't have the fact that I fulfill the itoisometry, and I won't have the fact that I am square integrable martingale. Okay, so I have a general definition, but I lose, the price to pay is to lose a lot of properties fulfilled by the stochastic integral in the case where x belongs to L2 prop. Okay, so we are going to admit this proposition. Okay, and now, in fact, I have a new integral, let's say, an extended one that coincides with my previous one for x in L2 prog. And keep in mind that, I have defined ito processes. I have defined ito processes from a constant plus a Riemann integral plus a stochastic integral. if I have an extended notion of the stochastic integral, I will have an extended notion for the notion of Ito process. So it's exactly the aim of this definition. So what I will call a generalized Ito process will be something that will be adapted and continuous, and that fulfill this decomposition with this one that is a number. And I have here a Riemann integral and a stochastic integral. For my Riemann integral, the minimal hypothesis will be to be in H1 lock here. And for the stochastic integral, but the minimal hypothesis I have is to fulfill this condition here, that is belongs to H2 lock. Okay? And so I define this way a generalized Ito process through the generalization of my stochastic integral to the case of H2 lock. And once again, I will use exactly the same differential notation, okay, in order to say that this process has this Ito decomposition. I will use the differential notation. Why not? Okay. So I have this. What is nice with this one is that, okay, all the things that I have proved previously are okay. I won't do the proof, but it is okay. In particular, if I consider the notion of extended Ito process, the Ito decomposition is unique up to stochastic equivalence, in the sense that if you have two decompositions, okay, of the previous type for xt, the constant are equals, the process psi and psi prime are indistinguishable, and the process phi and phi prime are indistinguishable. Okay, so I have unicity even in this generalized case. Okay, it's the aim of this proposition. Secondly, okay, the fact that if you have a generalized Ito process that is a martingale, necessarily, okay, so if I come back to the previous slide, okay, if I have a process of this form, okay, a generalized Ito process that is a martingale, necessarily the part in dt here, the Riemann integral part has to be equal to 0. It's exactly what I have proved, okay, in the case of an Ito process, and that can be extended easily using the same kind of proposition, that is the analogous of proposition 0.5.5, okay, in this framework, telling that martingale implies the part in dt is equal to 0. So I don't have a Riemann integral part in the case of a generalized Ito process that is a martingale, okay? And what is more, and that's why we have done the job this way, okay? So let me continue, is that in this setting here, okay, so let me have a look on what I want to do. So in this setting here, I have the following. I have the Ito formulas, so the one I have stated previously, the same. The only thing that is different here is that now I have exactly the same formula, exactly the same formulas in the case where f depend only on x, or in the case where f depend on the time and on x. But here, contrary to what I have said previously, so in the previous statement, okay, I need for f some strong conditions that are to be regular in the sense that they are C2, or C1 in the first variable and C2 in the second one. But in the previous statement, I need them with bounded derivatives. I need them with bounded derivative. And now, what is nice with the notion of generalized Ito process is that I don't need the fact that f prime and f second are bounded, okay? So just let me explain you why. So in the previous case, okay, the fact that I impose for f prime and f second to be bounded was in order to give sense to the Riemann and stochastic integrals involved in the Ito formula. Okay, here I have extended the notion of stochastic integral, and so I have extended the notion of Ito process, and you will see that now I can realize my hypothesis on f in order to make all these integrals well defined. So let's see, for example, so this case. So I have my Ito formula, and in fact, I have three integrals. I have this Riemann integral here, this one. I have, so keep in mind, this one is defined this way. It's an integral with respect to an Ito process. So you have another Riemann integral here, and you have a stochastic integral here, with my condition that is f is C2 from R into R. Okay, from R into R. Okay, and my integrability hypothesis for my Ito process X is that, okay, I have d of xt that is equal to of t dt plus phi, so it's not phi here, I use the same notation as previously, that is psi of t dt plus phi of t dbt, so in the extended way, meaning that for this one, I have this one in H1 log, and I have this one in H2 log, okay? So I have this. Okay. So what happens if I want to give sense to these three integrals here? Okay, so let's apply the argument for one because the argument will be the same for the other one. So let's consider, okay, this integral, the stochastic one here, this one. So I have inside S gives f prime of xs phi of s, okay, with phi that is in H2 log and f that is of class C2 here. And if I want to give sense to this integral here, to the stochastic integral, I have to check if this one, okay, I don't know if this one belongs to H2 log under my condition. But why I have this? But I have this because, okay, what can I say about this? Here, I have a mapping, okay, that is a trajectory, let's say, of my process. That is something that is continuous on 0 capital T. So I have something that is bounded. But be careful because here, okay, you have here a random variable here. You have a random variable, so that depends on W. So you have a bound, okay, a bound depending, of course, on W that belongs to omega. But, okay, for each W, I know that this mapping is bounded. Okay, for each W, this mapping is bounded because it is continuous on 0 capital T. So it implies that the probability that f prime of xs, okay, is finite, this probability is equal to 1. And in fact, more than this, okay, the probability that, okay, I can write it this way, the probability that the supremum, I can take the infinite norm here, is finite. This probability is 1 because I have something that is bounded. And so, if this one is bounded with probability 1, but if I have this one, so here you have something that is bounded with probability 1, you have here something that is in H2 log, and so necessarily, if you consider the integral of f prime of xs square phi of s square ds, the probability that this one is finite will be equal to 1 because, I repeat, this one has a supremum that is finite p almost surely. And so I have exactly this one. So under the condition that is f is simply of class C2, and here I just use the fact that f prime is continuous here. If f prime is continuous, this one is well defined. using exactly the same argument, I can prove that since f prime is continuous, this one is in H1 lock, and so this Riemann integral is well defined. And since f second is continuous, okay, this one is also in H1 lock, and so the Riemann integral is well defined. Okay, so my new extension of the Riemann of the the stochastic integral allow me to relax the hypothesis in the framework of the Ito formula. Okay. And the price to pay, I repeat, to this extension is that in general, okay, the stochastic integral that you will have here, this stochastic integral won't be a continuous and square integrable martingale, but whatever, it's something that is defined, okay, and I can apply this formula that give me, in fact, the Ito decomposition of a function of xt in terms of the Ito decomposition of xt, okay? So in other words, okay, this proposition tells you that if you take a regular mapping of a generalized Ito process, you obtain a generalized Ito process. Okay, and I have, of course, the same definition in the case where f is time dependent. So now it's nice because, okay, it's nice because in particular, I can apply the Ito formula to the case where that f is equal, for example, to the square mapping, because the square mapping is of class C2, or the exponential mapping that is of class C2, and so on and so on. Okay, I don't need the strong hypothesis that f prime and f second are bounded. Okay, and we are going to see now. Okay, so you have here, okay, this one. So just let me do this, what I have done here. So yes, let's spend time on this one. Okay, so a formula that we will use, okay, a lot of times in the following part of the course. That is what we call the integration by part formula. Okay, we are going to do the proof of it. It's what we call the integration by part formula. Okay. So let's see what happened. Okay, so I have two Ito processes, so two generalized Ito processes. That is here, okay, I have xt that is equal to x0 plus the integral between 0 and t, psi of s ds, the integral between 0 and t, phi of s dbs. And now I know that psi has to belongs to H1 lock in order to make this Riemann integral well defined. And through the extension I have supposed to be okay for the Ito integral, I can suppose it in H2 lock. So I have this generalized Ito process, okay, and I have also this other one, yt that is equal to y0 plus the integral between 0 and t of psi of s ds, so I put a prime here, plus the integral between 0 and t of phi prime of s dbs. And the same, I need the same for phi prime, that has to belongs to H1 lock. Huh? Here, prime is not for the derivative, huh? It's just for other psi and other phi here. And phi prime here belongs to H2 lock. So I want to obtain this formula here. That is, in fact, the Ito decomposition of the product. Okay? So what is the meaning of this one, in fact? If I write it using the differential notation, I have that d of xt yt, consider this way, is equal to what? Yt d of xt plus xt d of yt plus phi of t phi t prime dt. And in fact, this kind of formula is not completely new, because the beginning here is the classical formula in the sense that the derivative, let's say, of a product, so the derivative of uv is u prime v plus u v prime, u prime v plus u v prime. So here, okay, you have the beginning of the derivative of a product, okay? But since we deal with Ito processes, okay, you will have an extra term, as we have an extra term, okay, is the Ito formula for the Brownian motion, for example. And we know that this extra term comes from quadratic variations, in fact. And here I have an extra term that is what here? That is just the product of the quantity involved in the stochastic integrals for the decomposition of x and the decomposition of y. Okay, so it's an important formula to know, the integration by part for generalized Ito process that we are going to prove now. And the idea is to use the following. The idea is to say that, okay, if I do the sum, I know what is the Ito decomposition of the sum. I can write it x0 plus y0 plus the integral between 0 and t of phi plus phi prime of s ds plus the integral between 0 and t of phi plus phi prime of s dbs. And we are going, in fact, to apply the Ito formula, okay, not this one, but this one, the Ito formula here for f of x equal to x squared. Okay, so I applied 3 times the Ito formula to all these Ito processes. So I have here 3 generalized Ito processes. And we are going to apply 3 times the Ito formula that I apply for f of x equal to x squared. So in particular, we know that f prime of x will be equal to 2x and f second of x will be equal to 2. Okay, so I apply the Ito formula for these 3 Ito processes. So what I obtain if I do this? For the first, I obtain that x t square is equal to x0 square plus the integral between 0 and t of what? Of f prime, so that is 2xs d of xs plus 1/2 the integral between 0 and t, so of f second, that is equal just to 2 here, multiply by what? So if I come back to the previous formula, multiply, so f second is equal to 2 in this situation, multiply by the square of the term involved in the stochastic integral. So that is here, this 1 square, phi s square ds. So this is the Ito formula for x, applied to the square function. I do exactly the same for y. So if I do the same here, I obtain simply, in fact, the integral between 0 and t phi of s prime square ds. And if I do the job for the sum, I obtain x0 plus y0 square plus what? 2 times the integral between 0 and t of xs plus ys d of xs plus ys plus the integral between 0 and t of phi plus phi prime s square ds. Okay, so what I have written here, it's 3 times the Ito formula, okay, for these 3 generalized Ito process applied for f of x equal to x squared. Okay, so I applied 3 times the same formula and I obtained this. So how to conclude? To conclude, I will just remark that have this. So I erase this one here. I have this. And I just keep in mind the 3 Ito formula I have written previously. So what I obtain for this one. So here, I obtain from this one the following. So what we are going to take in mind, keep in mind that I want to have xt, yt. But I remind you that the product xy can be written as the following. So I can write it as x plus y square, okay, minus x square minus y square over 2. It's just by developing the square of the sum, I obtain exactly this one. X square plus 2xy plus y square. I subtract the square and I divide by 2. But if I do this, I obtain here xt, yt using this one. So I use, okay, let's write it one time. Xt plus yt square minus xt square minus yt square over 2. And if I do this, replacing xt plus yt square by this expression, replacing xt square by this expression, and replacing yt square by this expression, you will obtain, do the computation at home if you are not totally okay with what I've done here, okay? Then you obtain here exactly what I want, that is xt yt that is equal to, so I obtain xt yt that is equal to x0 y0, okay, plus the integral between 0 and t of y of s d of xs plus the integral between 0 and t of xs d of ys plus the integral between 0 and t phi s prime ds. Okay, I repeat that in order to obtain this, you replace xt plus yt square by this expression here, and then you are going to develop the square here and to develop the term here. You subtract with xt square and yt square, so you will have simplifications. Typically, if you just have a look on the constant, okay, x0 plus y0 square minus y0 square minus x0 square over 2 will give you this one. Okay, if you take this term here and you do minus this one over 2, you obtain exactly this term. And the same for if you take this one, subtract this one, and divide by 2, you obtain exactly these two. Okay, so do this at home. And this formula here is very important, and you have to know it. Okay, very important in what we are going to do. It's the integration by part formula for generalized Ito process, and I am able to obtain it because, okay, if you see what I have written here, okay, then I have it for it's a consequence of the Ito formula or the generalized Ito formula that I can apply to the square mapping because I have relaxed the integrability condition in the definition of the stochastic integral. Okay, so I have this. So just a remark, because, okay, I need to finish the chapter 2, but I see that I don't have finished to do all the slides, okay, but I will continue like this because, okay, we have a last part. So let's do it, okay, this way. So I have a last part, that is the part in the course in the chapter 2.5, okay, that is devoted so to what we call stochastic differential equations. In fact, it will be a very short part here because I won't enter into too much details for this part. So stochastic differential equations. I remind you that in classical analysis, what we called a differential equation, so an ordinary differential equation, is defined this way as a relation between, let's do it this way, the derivative of a mapping and a function of this mapping. Okay, so it's what we call the first order ordinary differential equation. Okay, we have condition on F that will ensure the existence and the unicity of a solution. And for example, okay, if you take y prime equal to y, okay, what I know, but I know that in this case, okay, if I fix an initial condition, y is equal to a constant times the exponential mapping. Okay, so y of x here, y of x is just a constant times exponential of x. Okay, so it's an ordinary differential equation that is just a relation between a mapping and its derivative. So now, okay, repeat and remind that the Brownian motion is not differentiable. The stochastic integral with respect to the Brownian motion won't be differentiable, okay? But I have a notion of not a derivative, but of differential, the one coming from the Ito decomposition. And what we are going to consider as a stochastic differential equation, it's a relation involving a stochastic process and its Ito differential, let's say, okay? I repeat that I won't enter into too much details concerning this part, but maybe I will do deeply in all details, okay? I will study in all these days a stochastic differential equation that will be the one involved in the chapter 5 of this lecture notes, okay? So it's exactly what we are going to do here. That is the part concerning the geometric Brownian motion. The geometric Brownian motion. So remind that we have seen together the definition of the geometric Brownian motion. It was defined this way. St that is equal to x0, a number, exponential, okay, b minus sigma square over 2t plus sigma bt, okay? And what was nice with this geometry Brownian motion is that first we have seen together that since I am able to generate discretization of the trajectory of the Brownian motion, if I give you the parameters x0, b, and sigma, you will be able, applying this formula, to generate discretization of the trajectory of a geometric Brownian motion. We have seen also together that the expectation of ST, we have proved together that it was just x0 exponential bt, okay, from the result concerning the characteristic function of a Gaussian distribution. I obtained this, okay? So you have here the definition of the geometry Brownian motion. But when I see this, what I have, in fact, I can say that my geometry Brownian motion is just a function of the time here and of the Brownian motion itself, where here f t x is equal to what? It's equal to x0 exponential b minus sigma square over 2t plus sigma x. Okay, I have this. And what is natural to do when I have such an expression is to say, okay, I have seen something previously. Okay, I have seen the Ito formula for a generalized Ito process. I have the Ito formula for a generalized Ito process. The Ito process here will be the Brownian motion. So I can apply this formula, the one with time dependency, okay, apply to the Ito process given by the Brownian motion and apply to the mapping F defined this way, okay? So here, okay, I will apply Ito formula for F and xt that is equal to bt, with the fact that here d of xt will be 0 dt plus dbt with a 1 here. Okay, so let's do the job. Okay, so what can I say concerning this? So if I apply, I repeat this Ito formula here, this one, this one, this Ito formula, I obtain what? So I obtain the following. I obtain that f of t and of bt is equal to f of 0 and b0, okay, plus the integral between 0 and t of the partial derivative of f with respect to x at the point s, bs, dbs. My Ito process is the Brownian motion here, so I have dbs plus 1/2 the integral between 0 and t of the second derivative of x with respect to the variable x, s, bs, ds, plus what? But the term coming from the fact that I have a time-dependent mapping, that is just the integral between 0 and t, f prime of t, s, bs, ds. And if I want to handle in more details this expression here, but I just have to check what are the derivative of this mapping here. So let's write the things here. And I see easily that if I compute the derivative with respect to x, okay, what I do, I just make appear a sigma. So I have this one, f prime with respect to x is just equal to sigma f. If I do the second derivative, f second x is just sigma square f, okay? And the derivative with respect to t is just what? So if I compute the derivative with respect to t, I make appear this term here. Okay, so I have just b minus sigma square over 2 f. So if I write this, what I obtain? I obtain that st, that is equal to f of t and bt, is equal to f of 0, b0, that is just, okay, x0, plus the integral between 0 and t of this term, f prime being sigma f, I obtain sigma bs dbs, plus 1/2 f second, that is equal to sigma square bs ds here, plus the integral between 0 and t of b minus sigma square over 2 bs ds. And maybe I will see that I have some simplifications. I have some simplification, yes. I have the simplification between this term here and this one here. And at the end, I obtain that d of st, okay, I can write it this way, d of st is equal to sigma, oh, I have done just a misprint here, excuse me. So here, when I do this, f prime is equal to sigma f. If I applied f prime at s and bs, I obtain sigma of f of s and bs. F of s and bs is s of s. So here it's not b that I obtain. Here it's not b. Here it's not b. It's a s that I obtain here. S of s, s of s, s of s here. Okay. So if I continue my computation, I have d of st that is equal to sigma st dbt coming from this term here, plus plus what? Plus this term, that is plus st dt. So the geometric Brownian motion fulfill this relation. And what is this relation? It is a relation between the Ito differential of my stochastic process, S, and inside here you have S. And it's what we call the stochastic differential equation. So you have something of this form, a relation between the derivative and a mapping. In the case of the ordinary differential equation, it's the classical derivative involved in this expression here. Here it will be the Ito differential, in fact, okay? That is the notation I have introduced previously. So I have proved that the geometric Brownian motion fulfill this relation. Okay, I obtain its Ito decomposition through the use of the time-dependent Ito formula. Okay, this way, and I obtain this one that is called, in fact, this one is called the Black-Scholes stochastic differential equation. I denote stochastic differential equation by SDA by opposition with ODE that are ordinary differential equation. So stochastic differential equation, okay? So I have this. Okay, so the geometric Brownian motion fulfill this one. So just a remark concerning the geometric Brownian motion. Okay, so maybe I can duplicate this. I have it, okay. So let's erase what I have done here. So I can erase everything. I just keep in mind, okay, this ordinary differential equation and the expression of the geometric Brownian motion itself. So the geometric Brownian motion is given this way, and we have proved that it fulfills this equation here. Here we have seen together that, so from a proposition I have proved previously, that we can see that ST is a martingale if and only if what I have, if and only if, in fact, the part in dt is equal to 0. If and only if the part in dt is equal to 0. So it is, okay, the proposition 2.4.3 here. Proposition 2.4.3, okay, that give you this one is a martingale if b st dt is equal to 0, but st is a geometric Brownian motion. So I have, if my x0 is not 0, I have something that is always different from 0, and I have something that is equivalent to the fact that b is equal to 0. So this, the solution of this equation is a martingale, okay, if and only if I don't have a part in dt that is b equal to 0. But of course I have this because I can see it on this expression. Keep in mind that we have seen together that for b equal to 0 here, you have st that is equal to x0 exponential minus sigma square t over 2 plus sigma bt. And here, it's a process we have studied at the beginning of chapter 1 as a transform of the Brownian motion that is still a martingale. Okay, so we recover from the proposition 2.4.3, okay, using the property of the decomposition, the Ito decomposition in terms of martingaleity, we recover a very basic result that we have proved directly in the beginning of the chapter 1. Okay, so I have this. So now what we are going to prove, in fact, so we have proved that the geometric Brownian motion fulfills this equation, and we are going to prove that, in fact, the geometric Brownian motion is the only stochastic process that fulfills this equation. So we have proved here, if you want, the existence of a solution to this equation given by the geometric Brownian motion. What we are going to do now is to prove the unicity of this solution. So it's what I have called in the lecture's note the proposition 2.5.1 that tell you the following, okay? So for b and sigma belongs to R square. Okay, there exists a unique, in fact, in the sense of indistinguishability, okay, in the sense of indistinguishability, there exists a unique, okay, Ito process let's write it this way, xt fulfilling d of xt is equal to sigma xt dbt plus b xt dt. And of course, as all the differential equation, I need, if I want unicity, to fix the initial condition to be equal to x0. So there exists a unique. Keep in mind that I have the existence. The existence was proved in the previous slide, where I have proved that my geometric Brownian motion fulfills this. It fulfills the equation I want. Okay, so for the existence, it's okay. Unicity, the only thing I have to prove. So I will call this one by star. So let x fulfilling star. Okay, if I want to prove the unicity, since I know that the geometric Brownian motion fulfills what I want, I need to prove. So let x fulfilling this equation, let's prove that so let's prove that, in fact, xt and s are indistinguishable. So I want to prove that they are indistinguishable. Okay, but keep in mind that here I have here two Ito processes. In particular, they are continuous. They are continuous. And in this case, I know that if I have two processes that are indistinguishable, that are continuous, to prove that they are indistinguishable, in this case, it is sufficient to prove that for all t belonging to 0 capital T, in fact, the probability that xt is equal to st, this is equal to 1. Okay, so I have just to prove that xt is equal to st with proba 1 for any t, because this one means that xt is a version, or that x is the version of s. But if these two processes are continuous, from what we have done in the chapter 0, if x is a version of s and if x and s are continuous, it implies that they are indistinguishable. Okay, so I have simply to prove this one. And in order to prove this one, so to prove the probability that xt is equal to st equal to 1, okay, but we are going to prove, in fact, that xt over st is equal to 1 p almost surely. I have the right to do this because I know that this quantity here, this quantity is strictly positive. So to prove that I have the equality, I can divide by st and to prove this one. Okay, so we are going to prove this. And to prove this, what we are going to do, we are going to compute d of xt over st. We are going to compute the Ito differential of xt over st. Okay? So, in fact, and to do this, we are going, so I can write it this way. We are going to use what I have called the integration by part formula. That was, okay, the formula here. We are going to use this integration by part formula here in order to obtain the Ito differential of the product. My product here will be simply xt and 1 over st. Okay? So let's apply the formula. So I write a new page here. So what I want to do, I know that d of xt is equal to sigma xt dt. So I have its Ito decomposition plus sigma xt dbt. I have also that x0 is equal to x0. So I have this. St is the geometric Brownian motion. x0 exponential b minus sigma square over 2 t plus sigma bt. Okay, in particular, what is st minus 1? I can write it simply as 1 over x0 exponential minus b minus sigma square over 2t minus sigma bt. If I want to apply the integration by part formula to xt, the product of xt and 1 over st, I have already the Ito decomposition of this term here. If I want to apply the integration by part formula, I need the Ito decomposition of this one. So I need to apply the Ito formula to obtain the Ito decomposition of this term. And here I can write it as f of t and bt, this one, where f of t and x is equal to 1 over x0 exponential minus b minus sigma square over 2t minus sigma x. And I need, if I want to apply the Ito formula, the derivative. So the derivative of this one with respect to t is equal to what? So I have a minus here, okay? So it will be minus b minus sigma square over 2f. Fx prime is equal to what? It's equal to, I will have a minus sigma, so minus sigma f, and f second with respect to x is equal to sigma square f. Okay, so if I apply the Ito formula here, I obtain that 1 over st is equal to what? 1 over s0, 1 over s0 that is equal to 1 over x0 here, plus what? Plus, so just let me 1 second, please. I have to switch off my phone. Okay. I have this. Plus what? The integral between 0 and t of f prime of x dbs, of sbs dbs. So I have here just simply minus sigma 1 over ss dbs plus 1/2 the integral between 0 and t of f second, that is sigma square 1 over ss. So here it's the Ito formula applied to the Brownian motion. The term in front of dbt in the Ito decomposition is 1. So I have here time 1 square ds. And it remains the term with the derivative with respect to t. So I have integral between 0 and t of this term here. I just write it here this way. Minus B minus sigma square over 2, 1 over SS ds with a minus before here. So I have this one, and in particular, I can say that d of 1 over st is equal to what? So maybe I have some simplification. Let's see. So I have what here? I have minus sigma over ss dbs. So it's the only term in dbs, so I can write it. So I have minus sigma over st here dbt. And then I have this term. So I don't know if I have simplification. In fact, I don't have simplification, but I can write the things this way. It will be plus, so I have sigma square over 2 s of s, and here I have plus sigma square over 2 this one, so I have 2 sigma square over 2, that is just sigma square minus b, so sigma square minus b, okay, over st dt, if I don't have done mistake. So it's exactly what I obtained here, okay? And now I can apply. So I have the Ito decomposition of x. I have the Ito decomposition of the inverse of s. So I can apply the integration by part, and I will obtain what? I will obtain xt d of 1 over st plus d of xt 1 over st plus what? Plus the square, the product of the term in front of dbt in the Ito decomposition. So here, in front of dbt, I have sigma xt. Here, in front of dbt, I have this one. So here, I obtain, as an extra term in the integration by part formula, the product of this one, and so I obtain minus sigma square xt over st dt. And what can I do now? But now I can replace this one by this one. I can replace this one by this one. And if you do the job, do it at home, it's that I obtain 0. I obtain 0 for the Ito differential of xt 1 over st. This one implies that xt over st is in fact a constant. And what will be this constant? This constant will be the value at 0 that is equal to 1. Okay, so I have proved here, if you have a look on what I have done, proving that the Ito differential of this product is equal to 0. I prove that this product is constant, this constant being equal to 1, because x0 is equal to x0 and s0 is equal to x0 also. Okay, and so xt is a version of yt. Here, the equality is p almost surely. So xt is a version of st. And if I come back to what I want, in fact, proving that xt is a version of st, since I have two Ito processes that are continuous, they are indistinguishable. So I have proved this proposition 2.5.1. Okay, so I have this. And you will see that in the chapter 5, it will be this stochastic differential equation that is called the Black-Scholes stochastic differential equation that we are going to use in order to model, okay, the behavior of particular risky assets. Okay, that is an asset depending on randomness. Okay, so let me do some concluding remarks. Okay, so you will see in the lecture's notes. Okay, so I want you to read. Okay, so read by yourself. 252, okay, in the lecture's notes. So you have 252, let's say 2.5.3, 2.5.4. So what is this three parts? Okay, so here, this one is some comments on the general stochastic differential equation. Here you have, so keep in mind that we have seen together in the chapter 1 that the geometric Brownian motion is a Markov process. Here, Markov, you have the Markov property of solutions of stochastic differential equation. And here, how to generate solutions of stochastic differential equation using a computer. So why I don't do this in detail now? Because, okay, in the chapter 5 of this course, okay, I will use the geometric Brownian motion. Okay, and for the geometric Brownian motion, I have proved just now that it is the unique solution of the Black-Scholes stochastic differential equation. So I don't need general result, okay, to prove this, because I use simply the fact that I have done the proof of proposition 2.5.1. Okay, so this part for the geometric Brownian motion, okay, is done through property 2.5.1. This part in the case of the geometric Brownian motion is done in the end of the chapter 0, where I have proved that since the Brownian motion is Markov, okay, then the geometric Brownian motion is also Markov using the independence of the Brownian increment. And in the case of a geometric Brownian motion, the geometric Brownian motion is just a function of the Brownian motion itself. I am able, and I have explained to you how to generate a discretization of the Brownian trajectory. So if I am able to do this, I will be able to do the same thing for the geometric Brownian motions, meaning that in the process, in the case of the process that will interest me in the chapter 5, that is for my financial application, that is the good way to do and to deal with the Black-Scholes model. Okay, I have done all the job. Okay, and here you have more general remarks, okay, for more general stochastic differential equation. So just let me do some comments concerning, okay, this, typically this one here. So what we call the stochastic differential equation in what you are going to read. Okay, I have said to you that it will be just, okay, it will be just a relation between the Ito differential of an Ito process, okay, and its Ito process. So something that I can write in a general way, this one. So in particular, as an example, if B of Tx is equal to Bx, if sigma of Tx is equal to sigma x, I recover the Black-Scholes stochastic differential equation. So the stochastic differential equation coming from the Black-Scholes, okay, formula is just a particular case of something that I can define as a stochastic differential equation and define this way, a relation between the Ito differential and the process itself, okay? So I have this. So keep in mind that for ordinary differential equation, okay, okay, so what I have here, you see that in this equation, we have one part here, this one. That is, in fact, this one is an ordinary differential equation. This one is an ordinary differential equation with respect to the time. And you add here a part that is just in relation with the Brownian integral and the Brownian motion itself, okay? So I have this one. And in fact, what I will do typically in this chapter here is to find conditions on B and sigma to ensure existence and unicity of solutions. So if you have followed a course concerning ordinary differential equation, you know that in the case of ordinary differential equation, you have a very famous theorem that is called the Cauchy-Lipschitz theorem that gives you conditions on the coefficients of an ordinary differential equation in order to ensure the existence and the unicity of a solution. And what is very nice in the case of stochastic differential equation is that we have the same kind of result. So I want you to have a look, okay, on what I have defined in my lectures notes. So let me have a look on. So see by yourself the theorem 2.5.1, that is the analogous of Cauchy-Lipschitz theorem for stochastic differential equation. And you will see in this theorem, okay, condition of on my coefficients in order to ensure the existence and the unicity of a solution. And you will see that this condition on B and sigma are exactly the same as if you have followed a course on ordinary differential equation, the same that you can find in the case of ordinary differential equation. And these are, in fact, you have Lipschitz condition in the second variable and the fact that you want that the coefficients are sublinear. So I have a precise look. I won't spend time today on this one. I have a precise look on this one, okay, in the lectures note, okay. You have even the proof of this that is a little bit technical, okay, but you can have a look on it if you are interested in. You have the proof of this theorem in my lectures note. It is a little bit technical, okay, but you have this one, okay. So it closes for the moment the chapter 2. Okay, so I will record a video concerning the chapter 3. So the chapter 3 is a little bit particular because, in fact, it is just the two last technical results we are missing in order to be able to do the financial part, namely the Girsanov theorem and the martingale representation theorem. Okay, so it's what we are going to do in the next video, that is to do the chapter 3, and then I will start the financial part, because this way I will have all my necessary material in order to do in good conditions the Black-Scholes model. Okay, so in order to summarize what I have done today, I have introduced the notion of Ito process. Okay, we have seen that we have the unicity of this decomposition and the fact that if I have an Ito process that is a martingale, the part in dt is equal to 0. I have tell you that we have the analogous for Ito processes of the Ito formula for the Browne motion that I can extend in this case, okay, with the same ID for the proof, okay. But we have seen that in this Ito formula, we have very restrictive condition on small f. If I want to relax this condition, I need to enlarge the set of the integrands for the stochastic integral. So it's exactly what I have done in the little second part of the video, okay, where I have explained to you, not in details, but I have explained how it is possible to extend from L2 prog to H2 log the stochastic integrals. And also I have explained to you that there is a price to pay to do this. I lose, in fact, more or less all the properties of the stochastic integral. The only thing I keep, okay, that are still valid is linearity, continuity, the fact that I am adapted, okay? All the other, in particular the martingaleity, is lost, okay? But if I do this, I am able to define what we call generalized Ito process that have a unique decomposition, and where I am able to the generalized Ito formula And with this generalized Ito formula, what is nice is that the condition on small f is very large. That is, I just need regularity in terms of differentiability. F has to be C2, and if f is C2, I am able to apply this formula. We have deduced from this formula the integration by part formula for generalized Ito process that we have proved together. And using this integration by part formula, what I've done, I have proved the existence and the unicity of the solution of the Black-Scholes stochastic differential equation. And I have done some comment on more general stochastic differential equation. And I want you to read by yourself the end of the chapter 2. And in the next video, to conclude, I will do the chapter concerning Girsanov and the martingale representation theorems. So see you next week. Bye-bye.